Unit 6 Review. The purpose of this video is to review the topics in Unit 6. The topics are the centroid and moment of inertia of an area, finding normal stress in beams using the Flexure Formula, normal stress in beams subjected to biaxial bending, finding shear stress in beams using the Shear Formula, and shear flow in built-up members. Use the times shown to jump to a specific topic. First, the centroid and moment of inertia of an area. Finding the centroid and moment of inertia of a cross-sectional area is a required step in determining the normal and shear stresses in beams. Generally, we find the centroid of a cross-sectional area first. The centroid is the geometrical center point of an area and is also called the first moment of area. For simple shapes like triangles, rectangles, and circles, the centroid can be easily identified by their geometric properties. For composite shapes, we find the location coordinates of the centroid using the equations shown. To use the equations, we break the composite shape into simpler parts and incorporate the contribution of each part to the whole. Tables of geometric properties of simple areas are common in engineering resources, including the exam reference material. In this table, the centroid locations of several basic shapes are indicated with the letter C. In rectangles and circles, the centroids are located at the horizontal and vertical center points of the shapes. Note that for semicircles, the vertical dimension to the centroid is 4r over 3 pi up from the base. For composite areas, the centroids need to be found. Most of the cross-section geometries that we use for beams are symmetrical about the y-axis, and many are symmetrical about both the x and y axes. For cross-sections symmetrical about both x and y axes, the centroid is easily found at the center of the cross-section. For sections symmetrical about the y-axis only, the vertical location of the centroid needs to be found using the y-bar equation. The moment of inertia of an area is a cross-sectional property like area and is also called the second moment of area. The moment of inertia can be viewed as a measurement of resistance to bending. The moment of inertia is based only on geometry, not on material properties. For simple shapes like rectangles, circles, and triangles, the moment of inertia can be easily found based on geometric properties. For composite shapes, the parallel axis theorem is used to compute moment of inertia. Tables of geometric properties of simple areas typically include moment of inertia formulas. For circular cross-sections, the moment of inertia is the same regardless of the axis. However, for rectangular cross-sections and most other shapes, the moment of inertia formulas change depending on the axis. So one must be aware of which axis the moment of inertia is being computed for. This will be discussed more later in this video. The parallel axis theorem formula shown is used to find the moment of inertia of composite shapes by breaking the shapes into simpler parts and incorporating the contribution of each part into the whole. For composite shapes that are symmetric about the moment of inertia axis, shown here as the horizontal axis, the moment of inertia can be found by subtracting the moment of inertia of the hollow regions from the moment of inertia of the perimeter geometry. Note that for these shapes, the centroids of the subtracted regions lies on the axis of the centroid of the whole shape. Therefore, the variable d in the parallel axis theorem formula is 0, and therefore the AD squared term is 0. Compare that to the T-shaped section shown. Unlike the I-shaped section, the T-shape cannot be found simply by subtracting the side rectangles from the bounding rectangle. This is because the centroids of each are not on the same horizontal axis, and the dimension d is not equal to 0. Therefore, the AD squared term must be included. In this problem, I'm going to find the vertical distance to the centroid, y bar, and the moment of inertia about the z-axis, iz, for the following cross-sections. I have two cross-sections, Section A is a channel shape, and section B is a hollow rectangle. And I'll start with A first. I have a couple of ways to solve this problem and find the location of the centroid and the moment of inertia of this channel cross-section. The way I've decided to do it is I'm going to break it up into 3 rectangles. And I'm going to find the location of the centroid from the bottom of the cross-section shape. So I've shown y bar, that's the dimension I need to find. Another option is to take the outside rectangle and subtract off the inside rectangle. That is another option, though I'm not going to use that one. And this is the equation I'm going to use to find y bar. And to solve this problem, I'm going to use a table. It may not be totally necessary for this simple problem, but I thought I would do it anyway as a review. Now that I've divided the cross-section into 3 parts, I'm going to find the base and height dimension of each part. The centroid of this cross-section lies on the z-axis. And that's the same axis we're finding the moment of inertia about. So, as a rule, the base dimension of any of our shapes is always going to be parallel to the axis about which we are finding the moment of inertia, so the z-axis. So for piece 1, for example, which is this rectangle, the base dimension is going to be 10 millimeters, and the height dimension is going to be then perpendicular to the axis we're finding the moment of inertia about. It'll be 80. For piece 2, the base dimension then is going to be 110 minus 10 on each side, that's 20, so that'll be net 90. And its height is 10 millimeters. And piece 3 is identical to piece 1. The next thing I need to find is the location of y tilde. Now y tilde is the centroid of the piece, as measured from the same axis we're finding y bar. And I've decided to find y bar from the bottom of this cross-section. And so I'm going to find y tilde relative to the bottom of the cross-section. For example, in piece number 1, y tilde is 40 millimeters up from the bottom. And that's the same for piece 3. For piece number 2, the location of y tilde is it's 80 all the way to the top, and then I come back down half of 10, that's 5, so 75 millimeters from the bottom of the cross-section up to the centroid of piece 2. And once I have those 3 values for each of my pieces, the rest is kind of just plug and chug, so let's go ahead and go through it. The next column, I'm going to calculate the area of each piece, that's just base times height. And the next column, to get the centroid, this will be the last column I need for the centroid, I'm going to multiply the area times y tilde. Now to calculate y bar, the vertical location of the centroid, I'm going to use this equation. I need to sum up all of my area values, I need to sum up all of my a times y tilde values. And I calculate y bar by taking the sum of a y tildes divided by the sum of the a's. And I get 52.6 millimeters exactly. Now I'm going to use the parallel axis theorem formula to find the moment of inertia of this composite cross-section. And what this formula says is I find the moment of inertia of each piece about its own centroidal axis, and then I transform it to the z-axis. That's what the AD squared term does. And you see we've already got A, that's just area, we can recycle that. But we need to find moment of inertia and D. So let's add that into our table. For moment of inertia, I'm just going to use this equation. The base times the height cubed over 12. And if I've correctly defined my base and height, using the rule previously mentioned, then I just plug in my values. Now I need to find my D term. D is the distance from the centroid of each piece to the z-axis. For example, on piece 1, it would look like this. That would be D1. And I can find that by just taking y tilde and subtracting off y bar. And I'll take the absolute value because sometimes these come out negative. It doesn't matter really because the D gets squared, but I like seeing the absolute value. So we can see D is just 12.6 millimeters for pieces 1 and 3, and for piece 2 it's a little bit farther from the centroid to the z-axis. It's 22.4. And now for my last column, I'm going to compute the AD squared term for each piece. That'll just be my area times my D squared. Don't forget to square it. It makes a difference. And now to compute the moment of inertia of the composite cross-section, I need to sum all of my moment of inertias for the individual pieces and sum all the AD squared terms and then add those two sums together. And I get a really big number, 1.6 million millimeters to the 4th power. And I could have converted to meters from the very beginning And that's fine to do, though those little tiny numbers, when using metric units, their little tiny numbers are kind of hard to deal with. So I like to leave it in units of millimeters. And then in the end, the very last step, convert it to meters. And I convert it to meters to the fourth power by dividing by 1,000 to the fourth power. And now I get a very small number. And that's typical for moments of inertia for cross sections of the kinds of shapes we use in engineering when using SI units. So for part A, I found my centroid location vertically, and I found my moment of inertia about the z-axis. Now I'm going to do the same for part B. Now the cross-section for part B is a lot simpler shape to handle, and here's why. The cross-section is symmetric, both about the y and z-axes. That means the centroid is right smack in the middle. So I know my distance y bar from the bottom of the shape to the z-axis is 2.5 inches, half of 5. The moment of inertia is easier to calculate too. I can take the moment of inertia of the outside rectangle and subtract the moment of inertia of the inside rectangle. There is no AD squared term that I have to worry about. And that is because the d in the AD squared term is 0 because the centroid of the inside rectangle falls on the centroid of the whole cross-section. So essentially I can calculate the moment of inertia with the parallel axis theorem with this equation. The moment of inertia of the outside rectangle is the base, 3 inches, times the height, 5 inches, cubed, divided by 12. Notice the base is parallel to the axis we're finding the moment of inertia about, which is the z-axis. The wall thickness for each wall is given as 0.5 inches. So the inside rectangle will have a base dimension of 3 minus 2 times 0.5, so it'll be 2 inches, and the height will be 5 minus 2 times 0.5 inches, so that'll be 4 inches. And now I have the location of my centroid and my moment of inertia about the z-axis. Normal stress occurs in beams subjected to bending, or in other words, normal stress results from an internal bending moment. It is sometimes called the bending stress. The Flexure formula is used to calculate normal stress at a point on a cross-section subjected to a bending moment. Normal stress, shown with the symbol lowercase sigma, will be positive, indicating tension, or negative, indicating compression, depending on the point of the cross-section evaluated. Note that the variable m is the internal moment on a cross-section and is constant at all points on a cross-section. The moment is often found from a moment diagram and can be either positive or negative. The axis the moment is acting about is the neutral axis of the cross-section and passes through the centroid of the cross-section. The variable y, which can be positive or negative, is the perpendicular distance from the neutral axis to the point where stress is being evaluated. The variable I is the moment of inertia of the cross-section about the neutral axis. It is constant for any point on the cross-section. The Flexure formula is based on a particular coordinate system. Consider the simply supported beam. Suppose the transverse loads acting on the beam all occur in the vertical plane shown. We assume the plane of the transverse loads is the xy plane. Here is the corresponding coordinate system. Note that the x-axis is the longitudinal axis of the beam. It is located at the beam cross-section's centroid. The y-axis is in the vertical direction, and the z-axis is perpendicular to the plane of the loading. For any cross-section on which normal stress is being evaluated, the plane of the cross-section is the yz plane. An internal moment acting on a cross-section of the beam acts about the z-axis of the cross-section. Therefore, the z-axis is the neutral axis of the cross-section. The negative sign in the Flexure formula is based on the sign conventions used in this class for tension and compression, internal moments, and the y-axis previously described. When a section of a beam is subjected to a positive moment, the beam bends into a concave upward shape, like a smile. On the neutral axis, which is really the xz plane, there are no stresses. Above the neutral axis, in the positive y region of the beam, a point on a cross-section experiences compression. The negative sign in the flexure formula causes sigma to be negative here. Below the y-axis, in the negative y region of the beam, a point on the cross-section experiences tension. The negative sign in the flexure formula cancels the negative sign on the y variable, resulting in a positive value for sigma. Let's look at a cross-section of a beam subjected to a positive moment. Note that when the positive moment is depicted as a curved arrow on the right side of the cut beam, it is in the counterclockwise direction and points to the compression side of the section. The normal stress distribution is shown on the cross-section, with compression above the neutral axis and tension below the neutral axis. Note that the distribution of stress is linear on either side of the neutral axis. As the magnitude of the variable y increases, the magnitude of the normal stress increases. Stress is maximum on the cross-section at the furthest distance from the neutral axis. In a cross-section symmetrical about the neutral axis, the maximum tension and compression stresses are equal in magnitude. For cross-sections that are not symmetrical about the neutral axis, the maximum tension and compression stresses are not equal in magnitude, and the maximum stress will be found at the point furthest from the neutral axis. Here's a cross-section of a beam subjected to a negative moment. Beam sections subjected to negative moments bend into a concave downward shape, like a frown. Note the negative moment can be depicted as a curved arrow in the clockwise direction, pointing to the compression side of the cross-section. With a negative moment, the tension and compression sides of the cross-section switch places in comparison to the positive moment. In the bottom half of the beam, the variable y in the flexure formula is negative. With a negative moment and a negative sign in the formula, the stress is computed as negative, or compression. I have an example problem that says, determine the maximum normal stress in the beam. We see in our beam that it is simply supported with a pin on one end and a roller on the other. There's a distributed load. It's uniform over its full length, 800 pounds per feet. And right in the middle there's a point load, 1,200 pounds, and the beam is 4 feet long. We're also given the cross-section. It's an inverted triangle. Its width is 2 inches and its height is 3 inches. I'm going to use the flexure formula to find the normal stress. To find the maximum stress, I need the maximum moment, and I also need the furthest distance from the neutral axis. So let's get the moment first by drawing the shear and moment diagrams. Here's a free body diagram of my beam. I wanted to point out something. We've got a symmetrical beam here. Even though we have a pin and a roller on the two ends, the support reactions are symmetrical, and the load is symmetrical. And that means the reaction forces are going to be symmetrical as well, or equal. And so to find the reaction forces, I don't need to sum moments. I can sum up the total load on the beam. I calculate that's 4,400 pounds. And then I just divide that by 2. I get 2,200 pounds. And that's the support reaction on each side. I have my shear diagram. And here's my moment diagram. The moment is parabolic on both sides. It doesn't go to zero slope because of this change we get in our shear diagram. I need to find the maximum point on the moment diagram. And so I'm going to look at the shear diagram for that. And I can find it by taking the area under the triangle and adding that to the area of the rectangle on one side of the shear diagram. Here's the area of the triangle, here's the area of the rectangle. I get 2,800 pound-feet. And notice that's positive, and that is my maximum moment. I've redrawn the cross-section of this beam so we can get another look at it. I found this geometry for a triangular area in the exam reference material. Note, it gives the location of the centroid. It's going to be 1/3 of the height up from the base. The base is the horizontal portion of our triangle, so that means that the centroid is going to be down 1/3 the height from the base for our triangle, and that is going to be 1 inch. So the neutral axis passes through the centroid of the cross-section. And it's useful to know that because when we calculate the variable y in our flexure formula, it's going to be based on the location of the neutral axis. Also from the exam reference material, we get an equation for the moment of inertia of the cross-section. It's 1/36 times the base times the height cubed. And that is 1.5 inches to the 4th power for our cross-section. Now I'll use the Flexure Formula to solve for maximum stress. Our maximum moment is 2,800 pound-feet. That's positive. I convert that to pound-inches by multiplying by 12. Our moment of inertia in the denominator is 1.5 inches to the fourth power. Since we're looking for maximum stress, then our variable y is going to be the distance to the point on the cross-section furthest from the neutral axis. If we look at our cross-section, we see that the point on our triangle is the furthest point from the neutral axis, and it's 2 inches below the neutral axis. So in the Flexure Formula, I say that y is negative 2 inches, and is negative based on our sign convention. And the answer comes out to be a positive 44,800 psi. It's positive because the negative sign on the y and the negative sign out in front of the equation cancel out. And that means that the point on the cross-section is in tension. And that's what we expect since it's on the bottom side of the beam, and the beam is subjected to a positive moment. Its deflection will take the shape of a smile, and that means it's getting compressed on the top and stretched on the bottom. And if it's stretched on the bottom, then it's feeling tension. When a beam bends about 2 axes simultaneously, it is called unsymmetric or biaxial bending. This can occur when a beam is loaded in its 2 transverse principal planes. It can also occur from a single load acting between its principal transverse planes. In this case, the load can be split into components acting in the principal transverse planes. Let's consider the beam loaded in both the horizontal and vertical planes, but analyze them one at a time, starting with the vertical load. When we slice through the beam, we see a moment acting on the cut surface. The moment is acting about the z-axis. As was done in your statics course, we can represent the internal moment with a vector pointing in the z direction. The small curved arrow around the vector is added to show that the vector represents the right-hand rule. If the thumb on your right hand points in the direction of the vector, your fingers show the rotation direction. The right-hand rule is always used for moment vectors in this course. Now let's consider loads acting in the horizontal plane. When we slice through the beam, we see a moment acting on the cut surface. The moment is acting about the y-axis. We can represent the internal moment with a vector pointing in the y direction. Again, the vector and curved arrow represent the right-hand rule. When a cross-section is subjected to biaxial bending, a complicated distribution of normal stress occurs. However, it is easier to analyze the distribution of stress as the superposition of stress distributions from separate moments occurring about the z and y axes. The normal stress equation shown combines stress from a moment about the z-axis with the stress from a moment about the y-axis. The first term in the equation is the standard Flexure formula previously discussed. The z subscript on the moment indicates that the moment is occurring about the z-axis. It can be found by multiplying the applied moment by the cosine of theta, where theta is measured from the positive z-axis and is clockwise positive. The z subscript on I indicates that the moment of inertia is taken for the z-axis. For the second term, the y subscript identifies the direction of the moment and indicates the axis for the moment of inertia. The moment my can be found by multiplying the applied moment by the sine of theta. The y and z variables are the coordinates of the point you are calculating stress based on the cross-section coordinate system shown. Care should be given to ensure that correct signs are used on both moments and the y and z variables. The neutral axis of the cross-section, where the normal stress is 0, can be defined by the angle alpha. Alpha is computed using the equation shown. The neutral axis passes through the section centroid. Alpha uses the same convention as theta, clockwise positive, and measured from the positive z-axis. Here's an example of an unsymmetric or biaxial bending problem. It says, determine which corner feels the maximum compressive stress from the applied moment, which is shown as a vector in the YZ plane. You can see the moment vector shown in red It has a magnitude of 2 kilonewton meters. We can visualize its direction using the right-hand rule. The cross-section is the cross-section of a beam. It is a hollow rectangular shape. The units shown are in millimeters, and the wall thickness is given as 15 millimeters. Since we are looking for the corner with the maximum compressive stress and not the value of stress, this problem can then be solved conceptually. It can also be solved numerically. I'll do both. Let's look at the conceptual solution first. I've split the applied moment into its z and y components, showing them as vectors. Let's consider the z-direction moment first. The z-direction moment vector is shown on the z-axis. This means that the z-axis is the neutral axis for this vector. On one side of the neutral axis, the stresses will be in compression. On the other side, they'll be in tension. The vector is a representation of the right-hand rule. If we put the thumb of our right hand in the direction of the vector arrow, the curl of our fingers shows the direction of the moment on the cross-section. Visualize it as our fingers pulling on the top half of the cross-section and curling around and pushing on the bottom half of the cross-section. Thus, the bottom half of the cross-section is in compression. Let's use the same logic for the y component of the moment on the right. For the y component of the moment, the y-axis is the neutral axis. This means that the portion of the cross-section on one side of the neutral axis will be in tension and the portion on the other side will be in compression. Applying the right-hand rule, our fingers pull on the right side of the cross-section and curl around and push on the left side. Thus, the left side of the cross-section is in compression. There is only one corner that feels compression in both scenarios. Therefore, corner D will be the corner that feels the maximum compressive stress from the applied moment. Now, let's solve this problem numerically. The first thing I'm going to do is find the angle theta. Theta defines the location of the moment vector from the positive z-axis, going clockwise positive. I can calculate the angle to be 360 degrees minus 90 degrees, which is the lower left quadrant, and then minus 35 degrees, which is the angle shown to the moment from the y-axis. And it's positive. Once I know theta, I can find the moment component about the z-axis by multiplying the moment times the cosine of theta, and I get negative 1.147 kilonewton meters. I find the y component of the moment by multiplying the applied moment by the sine of theta, and I get negative 1.638 kilonewton meters. Notice that the sine direction on both moments is consistent with the coordinate system. The z component of the moment is pointing in the negative z direction, and the y component of the moment is pointing in the negative y direction. Next, I find my moment of inertia values. I need the moment of inertia about the z-axis. So I'm going to take as my base the dimensions that are parallel to the z-axis. So I will compute my moment of inertia as the outside rectangle minus the inside rectangle. The base of the outside rectangle is 150 millimeters, and the height is 90. And the base of the inside rectangle will be 120 millimeters, and height 60. I also find my moment of inertia about the y-axis. I will use the same procedure, subtract the inside rectangle from the outside rectangle. This time, the base and height dimensions switch places. Here's our stress equation, and here I've filled in the values that we calculated so far. For mz, I converted the units to Newton meters, and notice I've kept the sign on it. The same is true for my. I've also included the moment of inertia values. We're interested in the corner that is experiencing the maximum compression stress. To get the maximum compression stress, we need both terms in our equation to be negative. Remember that the y and z variables in this equation are the coordinates of the point where we are calculating stress. In the first term, the negative sign in front of the term and the negative sign on the moment cancel out. if I need the first term to be negative, then my y coordinate also needs to be negative. In the second term, the moment is negative, so the term will be negative if my z coordinate is positive. So I want to find the corner that has a negative y coordinate and a positive z coordinate. We can see from our cross-section that that would be corner D. It is in the negative y direction and positive z direction. So the answer to our problem is it is corner D. If I want to compute the maximum compression stress, I will plug in y and z coordinates into the equation. When I do, I find that sigma is negative 14.8 megapascals, and the problem is done. Shear stress occurs in beams as a result of the internal shear force. It is sometimes called beam shear stress. The shear stress at a point on a cross-section of a beam is determined using the shear formula shown. The variable V is the internal shear force on the cross-section and can be found from a shear diagram. The variable I is the moment of inertia of the cross-section about the axis perpendicular to the direction of the shear force. It is the same moment of inertia used for computing normal stresses caused by the same loads on the beam. The variable T is the dimension of the cross-section at the point where stress is being evaluated. It is measured perpendicular to the shear force direction. The variable Q is equal to an area, A prime, times the dimension y bar prime. It will be discussed further shortly. The shear formula is most accurate at points on a cross-section where the sides of the cross-section at the point are vertical. The shear stress acts in the direction of the force. Stresses are zero at the extreme edges of the section and increase in magnitude towards the neutral axis. The stress magnitude distribution has a parabolic shape. On a line perpendicular to the shear force direction, the shear stress is uniform. For any cross-section, the variables V and I in the shear formula are constant anywhere on the cross-section. For this rectangular cross-section, the variable T is also constant anywhere on the cross-section. This means that the shear stress magnitude is changing on the cross-section because the variable Q changes over the cross-section. Abrupt changes in the variable T result in localized jumps in stress. The variable Q is equal to an area, A prime, times the dimension y bar prime. A prime is an area above or below a line that passes through the point of interest. It always extends from the point of interest to the extreme edge of the cross-section. The line that defines the point of interest is perpendicular to the internal shear force, and the stress is constant on the line. Note that A prime is independent of the neutral axis. However, the point of interest is often taken at the neutral axis because this is often where shear stress is greatest. Y bar prime is measured from the neutral axis of the cross-section to the centroid of area A prime. A very useful property of Q is that it can be written in this form. It tells us that if the area A prime is a complex area, it can be broken into two or more smaller parts, and the total composite Q is the sum of the Q for each individual part. A common example of its use is finding the maximum shear stress in a beam made from a pipe. The maximum shear stress will occur at the neutral axis. The area A prime is then taken as half of the pipe cross-section. To find Q for this area, we can say that Q for the half pipe is equal to Q for the semicircle defined by the outside radius minus Q for the semicircle defined by the inside radius. Knowing the centroid of a semicircle is located a distance 4r over 3 pi from the horizontal base, we can compute Q as shown. The first term is the area A prime of the outside semicircle times its centroid, which is y bar prime. The second term is the area A prime of the inside semicircle times its centroid y bar prime. As previously mentioned, maximum shear stress often occurs at the neutral axis, but not always. To find the maximum shear stress, keep in mind these notes. Q is always maximum at the neutral axis. However, abrupt changes in the variable t cause jumps in the shear stress. Note from the shear formula that as the variable t decreases, stress increases. It is possible to have shear stress be larger at the change in width t. Consider the two T-shaped cross-sections. In the section on the left, the neutral axis, and thus largest Q, corresponds to the smallest t in the cross-section, so the maximum shear stress will be at the neutral axis. In the section on the right, the neutral axis, and thus largest Q, is in a region with a large t. At a short distance from the neutral axis, there is an abrupt decrease in thickness t. It would be prudent to calculate shear stress both at the neutral axis with the larger t value and at the top of the stem with the smaller t value to determine which location has the higher stress. Finally, a few more words about the variable t. T is the total width of all material on the cross-section at the line of interest. The material may be broken up as shown in these two examples. If we were computing shear stress at the neutral axis, where it is maximum for both cross-sections, the variable t would be equal to 2 times the dimension s. This example problem states, determine the maximum shear stress in the beam. We have a simply supported beam, with a pin at one end and a roller at the other. It is subjected to a uniformly distributed load. We're also given the cross-section. It has an I shape. I'm going to use the shear formula to solve this problem. I, Q, and T are all based on the geometry of the cross-section. V I'm going to take as the maximum shear force in the beam. I'm going to find it first. To find it, I will draw a shear diagram. Here's a free body diagram of the beam. The loading on the beam and the supports on the beam are symmetrical, so the two support reactions will be equal. I calculate that they are both equal to 22.5 kips. Here is the shear diagram for the beam. I can see that my maximum shear force in the beam is equal to the support reaction, 22.5 kips. Next, I will find the moment of inertia of the cross-section. I will find it by subtracting the inside rectangles on either side of the vertical web from the rectangle that describes the full perimeter of the shape. The units on this cross-section are in inches. Because the shear force is acting downward on this cross-section, then the neutral axis is perpendicular to that, so horizontal. And the base dimension is then the horizontal dimension, 8 inches, height is 14. And I'm subtracting off the two inside rectangles. I get my moment of inertia. The next thing I'm going to do is find Q. To find Q, I need to know where on my cross-section am I calculating stress. Let's look at the full cross-section. We know that Q is maximum at the neutral axis location, and that's usually the location of the maximum stress. But sometimes it's not. If we get an abrupt decrease in the thickness T, that can cause a jump in our shear stress. But we see that the neutral axis of this beam at the centroid aligns with the smallest cross-section dimension. So we can know with confidence that the maximum shear stress is going to be at the neutral axis, which passes through the centroid of the cross-section. So I've zoomed in on the cross-section and drawn the top half. And I'm going to take as A prime the area above the neutral axis, or the whole top half of the cross-section, and that has this T shape. Q is equal to A prime times y bar prime, and the A prime then would be the full area of the T, which would be relatively easy to calculate, but its centroid would be a little bit harder to find. So what I'm going to do is break up my area, A prime, into two pieces. I'll call the top flange piece, piece 1, and I'll call the web piece, piece 2. The area A prime of piece 1 is just the area of that rectangle. And its y bar prime goes from the centroid of A prime back to the neutral axis of the full cross-section, as shown. A prime 2 is going to be a rectangle, and its y bar prime dimension is from the centroid of that rectangle back to the neutral axis. And here's my calculation. A prime for piece 1 is 0.75 inches tall by 8 inches wide. And the y bar prime for piece 1 is the full 7 inches, that's from the centroid up to the top edge of the cross-section. And then I'm going to come back down just half of that 0.75 inch dimension. For piece 2, it's 6.25 inches tall and 0.5 inches wide, and the y bar prime is just half of 6.25 inches up. And I calculate Q. The units are inches cubed. And now I pull all the information I have together. My shear force is 22.5 kips. My Q was just found, about 50. I was previously found, 608.63. And now T. And T is the thickness of the cross-section at the point where we are computing stress. And that's right in the middle of our cross-section at the web, which has a thickness of 0.5 inches. And I compute that the maximum shear stress is 3.66 kips per square inch. And we're done. Now, shear flow in built-up sections. Shear flow describes the force that exists parallel to the laminations or components of built-up beams. When the T-shaped beam bends, shear flow occurs throughout each cross-section and is especially important at the joint between the flange and the stem. The shear flow causes these members to separate horizontally, as seen in the figure of a loaded beam on the left. Therefore, built-up sections should be designed to have sufficient strength to resist shear flow at the joints between the member components. The shear flow at any point along the length of a beam can be computed with the equation shown. Shear flow is given the symbol lowercase q and has units of force per distance. The variable v is the internal shear at the point being evaluated. It can be determined from the shear diagram. I is the moment of inertia of the full composite cross-section about the axis perpendicular to the internal shear force. Q is the same Q used in the shear formula. When determining Q for shear flow in built-up beams, the point of interest is always at a joint between beam components. For the T-shaped beam shown, consisting of a vertical stem connected to a horizontal flange with fasteners, the point of interest is the joint between these components. The area A' can be taken as the full flange piece, and y bar prime is the distance from the neutral axis of the composite cross-section to the centroid of A'. As an alternative, the area A' can be the full stem piece, and y bar prime is again the distance from the neutral axis to the centroid of A'. One thing to note is that the joint of interest for computing shear flow does not need to be perpendicular to the internal shear force direction. Suppose you want to compute the shear flow at the joint shown by the black and white arrows. The simplest way to solve this problem is to take the whole component to the right of the joint as A'. Y bar prime is the same as always, the distance from the neutral axis of the composite section to the centroid of A'. If components of a built-up beam are connected with a continuous weld or glue bead, then the shear strength of the weld or glue bead in pounds per inch or newtons per meter should be equal to or greater than the calculated shear flow. If members are connected with individual fasteners, then the equation shown can be used to compute the maximum permitted spacing between fasteners. In the equation, S is the longitudinal fastener spacing, or the distance between fasteners in the direction of the beam axis. C sub F is the capacity of a single fastener in shear. It has units of pounds or newtons and can be found from testing or manufacturer data. N is the number of fasteners in a single cross-section. For example, having 2 fasteners side by side doubles the load capacity. Lowercase q is the shear flow, calculated with the shear flow equation shown earlier. This example problem states, find the spacing S between fasteners to the nearest 10 millimeters spacing. The capacity of a single fastener is 800 newtons. We have a beam cross-section shown with an internal shear force acting on a cross-section of 3,000 newtons. We're given the dimensions in millimeters. And here's the spacing we're trying to find. It's the longitudinal spacing between sets of fasteners. So how far to the nearest cross-section with fasteners. And the capacity we were given of a single fastener, that's the shear strength capacity. It's 800 newtons. Here's the equation we're going to use. It's the shear flow equation. We know V, it's 3,000 newtons. We need to find Q and I. Let's find I first, the moment of inertia. To find I, we also need to know the location of the centroid. So I'm going to divide this cross-section up into pieces, find the centroid, then find the moment of inertia. So here's the cross-section, and I divided it into 3 pieces, and based on the dimensions, I'm able to calculate the location of the centroid from the bottom of the cross-section. I find that it is about 56 millimeters. That seems right. Continuing on my table, I can find the moment of inertia of each section and the AD squared term, and using the parallel axis theorem formula, I add those together and compute my moment of inertia for the composite cross-section. Next, I'm going to find Q. When we're looking at spacing between fasteners in a built-up beam, we're interested in the joint where the fasteners are located, because that's where the shear flow is transferring between pieces of the beam, and we want to make sure that those fasteners are sufficient to transfer the shear flow. So we're going to be looking at the joint, and that helps us decide what we're going to use for A prime. And we have 2 options. We can take the area above or below the joint, and as you see, I've decided to take the area for A prime as the top board above the joint. And the distance y bar prime will just be the location from the centroid of A prime back to the neutral axis, which we found a moment ago. So the area of A prime is just the area of that top piece. It's 20 millimeters tall, 120 millimeters wide. To find my y bar prime, I'm going to take the whole height, which is 90 millimeters. I'm going to subtract off 10 to go down from the top 10 millimeters to the centroid of A prime. And then I'm going to subtract off the y bar dimension that we found, 55.8, and that will leave me with the y bar prime dimension shown in the drawing. And if I divide my answer, which is in millimeters cubed, by 1,000 to the 3rd power, I can convert it into meters cubed. And now I can input the variables into the shear flow equation. The shear is our internal shear force, was given as 3,000 newtons, and the Q that we found just now, and I from above. And I can compute a value for shear flow. Note the units, they're in newtons per meter. And that's the force that's trying to separate the top board from the bottom 2 going into the screen. Every meter we accumulate 45,000 newtons of force. And that needs to be transferred through the nails. Each one of those nails can handle 800 newtons in shear. So we can use that information to compute our spacing. Here is our spacing equation. It's going to be the capacity in shear of a single fastener. That's C sub F, that's 800 newtons, times N. On the bottom is lowercase q, our shear flow that we just calculated. Let's talk about N briefly. N is the number of fasteners in the cross-section. Another way to think about it, though, to be more precise, it's the number of fasteners that penetrate that A prime boundary. And if you see in our cross-section, we have 2 fasteners penetrating the boundary. Suppose you have another fastener elsewhere in the cross-section. If that fastener does not penetrate the boundary of A prime, then it is not included in N. In this case, we have 2 fasteners, so N is equal to 2. And that's essentially doubling the shear capacity of the fasteners. And that makes sense. And I compute that our spacing cannot exceed 35.2 millimeters. So that's going to be the distance to the next cross-section going along the length of the beam. We'll go 35 millimeters, and then we need 2 more fasteners installed. Now, let's look back at the question. It asked us to find the spacing to the nearest 10 millimeters. So when it comes to spacing in fasteners, if we round up, we are decreasing the capacity of the beam to transmit shear flow. So for spacing, we need to round down. So the nearest 10 millimeters would be 30 millimeters. And that is our answer. This concludes our review of the topics in Unit 6.